Please welcome research scientist at the RIKEN Center for Computational Science, Dr. Miwako Tsuji.
So, welcome to this final invited talk session. It's my really pleasure to introduce two distinguished researchers in big data. So, the first speaker is Takemasa Miyoshi. He's a team principal at the RIKEN Center for Computational Science and team director at the RIKEN ISIMS. His research focuses on data simulations, numerical weather prediction, and fusion of HPC simulation with AI. His team's work on real-time forecasting was recognized as a finalist for the Golden Bell Prize for Climate Modeling. An author of more than 170 peer-reviewed publications, Dr. Miyoshi has received numerous awards, including Meteorological Society of Japan Award and the Ministry of Education, Culture, Sports, Science, and Technology. He received his PhD in meteorology from the University of Maryland. So please welcome Dr. Takemasa Miyoshi.
Okay, thank you very much. Thank you very much for this wonderful opportunity to be in this big room for the first time. I'm going to talk about our work using Fugaku for the weather forecast, but with a broader context based on these achievements. So just to start setting up the common background, this shows what happened in the past 150 years or so on weather prediction. So these technologies brought the innovations in weather prediction, particularly at the beginning, the real-time communication for the long distance enabled us to plot the weather map. We understood how weather moves. And then with the computing, we started the numerical weather prediction. As we all are computer scientists, know very well that the first generation electronic-based computer, we started the numerical weather prediction. And after we had big data from remote sensing, data assimilation, to how to use these data from massively, the scanning technology was a major challenge. So data assimilation has been playing a central role for set up the whole workflow of numerical weather prediction in the past, like 50 years or something. And then recently, as we all know, that the AI can do much more, much faster, and it's essential to think about how to combine these technologies. And this is another big picture on scientific paradigms. The left side is inductive, and the right side is deductive. The inductive means data-driven, and the deductive is basically theoretical and equation-driven. So we have first, second, and third, fourth sciences, and the first, second are based on the human intelligence, but the third and fourth based on computer power, basically. And we have this vision to build what we call prediction science, combining all of these four paradigms. Okay, so we have this supercomputer Fugaku at this moment in Kobe. We started the operations in March 2021, and at that year, we had Tokyo Olympic Games that was postponed by 1 year, but we had an access to this computer. So what we have been doing on data simulation, combining the big data with big simulations, was just to push all the limits of the computational wall. So we explored basically 2 orders of magnitude bigger computations and to explore what will be a choice of a future numerical weather prediction. So well, 2 years ago at SC25, that was my first time ever to participate in the supercomputing conference. I had a privilege to present our Gordon Bell Prize finalist paper on big data assimilation. So that presented basically what we did with this Fugaku during Tokyo Olympic Games. So we used exclusively the 7% of Fugaku with 500,000 cores. And using this new type of the remote sensing radar. So it's a multi-parameter phase array weather radar. We call it MP-PAR. And this can capture basically 100 times more data than the traditional type of weather radars. And here is the workflow. So we receive the data from the radar, and we immediately send the data to Fugaku. And then we have a software that takes the data continuously every 30 seconds, and then produce a forecast. So here is some image of our prediction. So what is unique here is the bottom right corner. You can see the time. And the time progresses at every 30 seconds. So because we have the data every 30 seconds, we get the data, and we take the data into our forecasting system, produce a forecast every 30 seconds. That's why the rain patterns, the red is more intense. The rain patterns looks like moving slowly, but it's because every 30 seconds, the quasi-linear, and that's why it looks slow, but it's actually evolved very rapidly. In 5 minutes, the rain patterns change quite significantly. Okay, so the Gordon Bell finalist was targeted on this time to solution. So we continuously run the system for 1 month period for the Olympic and Paralympic Games. On the left side, the panel is Olympic period, and the right side panel is Paralympic period. What is shown here is the time to solution. So 3 means 3 minutes. So within 3 minutes, most of the time, we could produce the forecast available for public up to 30 minutes at a later time. So this is a 30-minute lead time forecast produced within 3 minutes. So this type of the forecasting system never existed before, and this was our really first time to produce this type of very precise forecast of heavy rain. So this shows one case of our prediction. On the left panel, we show the 30 minutes lead time prediction, and the middle is the ground truth observed rain pattern. So we can see these heavy rain patterns are very well predicted 30 minutes in advance. And the rightmost panel shows the line, 2 lines, and the red is our new forecast system skill, higher the better. So our skill is clearly better than the baseline. And this is a volume image so that we can see precisely where you have the heavy rain occurring in Tokyo. So that blue part is the Tokyo Bay. And what is shown is a bird's eye view to these rain systems. So if we compare with other systems like Japanese or US, Canada, UK, France, and German, operational weather forecast systems, what is the biggest difference is the update frequency of 30 seconds. Compared with the other systems, the other systems are typically 1 hour, but 30 seconds is 120 times faster than 1 hour. So we compute 120 times more forecast on data assimilation within an hour. And why this is important? Because the convective rain system, those rapidly changing rain systems change quite rapidly, so that within 1 hour, the new rain occurs and die. That means that we cannot predict that kind of heavy rain locally developed. So our system is designed for the first time to capture those rapid development of the heavy rain. And we expanded this based on our achievement in 21 in Tokyo. We expanded our system to Osaka. There are 2 radars, as shown in this slide. This was another first time ever experiment that we used 2 radars at the same time. So we did 1 month, or a little less than 1 month period of this experiment, and we issued 75,000 forecasts, because every 30 seconds we issued a forecast. And that was similar to what we did during Tokyo Olympics. And what is the major difference is because of the 2 radars, we needed to expand the domain size, and that required basically twice as many computations. So we used 16% of Fugaku this time in August this year, and we could produce relatively in a stable manner for these type of heavy rain event. So this shows a case of the heavy rain well predicted 30 minutes in advance, so that we had this smartphone app having a push notification 30 minutes in advance that we have rain. So this is similar to what we saw in, for example, Back to the Future movie, when there was a dog opening the umbrella before the rain starts. So we could do this now. But that movie was, I think, in 2015, well, like 10 years before. The movie was produced in late 80s or something, I guess. But we can do this now. And this is a still image, 30 minutes lead forecast on the left, and the right side is the verification truth. And the red arrows show the site of Expo, the Osaka exposition in August 25. And we could produce this rain very well at that time, this heavy rain. And we have seen this type of the rain several times, and every time we could predict pretty well, although not perfect. So this shows the volume data of the rain, so that we could produce that. Of course, the rain on the ground, that's most essential. But we could also produce the upper level, the rain cloud in the sky for 30 minutes to the future. So we have explored these top science studies, and now we expanded our knowledge to develop the Argentinian operational weather service systems. So we have this project Prevenir to develop the weather forecast and the flood forecasting systems. So this is an idea of the digital twin of the weather, so that we can produce the current situation based on the monitoring and our background prediction data to project into the future, so that try to help people at this moment in 2 major cities in Argentina. One is Buenos Aires, and the other is Cordoba, the second biggest city in Argentina. And these are the pilot domains, so that we have a plan to expand our system to the broader regions. But this is just started in like 3 years ago, and we are now aiming at concluding the first phase up to 5 years. Okay, another thing that we have explored is the control, the concept of control beyond the prediction applied to the weather. We had so this is based on the idea of taking advantage of chaos to control. So because of chaos, there is a high sensitivity, so that we cannot predict. So because of the small change, it leads to a different future. So that's why prediction is difficult. Particularly for the heavy rain events or the typhoon or intense weather events are more difficult to predict because of the high chaotic dynamics, highly chaotic dynamics. Okay. But this implies we cannot tell what kind of small difference to make, because if we just make a small difference at the beginning, then that will lead to completely different future, then we cannot control. But that means that if we can make a small difference, if we have a method to select the desired trajectory among all possible different trajectories, then we could possibly control this chaos based on very small interventions. So that's a basic idea. And we developed a theory to do this. So there has been a lot of studies on chaos control, but all of those methods have, in my understanding, aimed at stabilizing the unstable orbit like this. So we have a very famous Lorentz three-variable model in this case. On the left side is the Lorentz attractor without control. So it goes to the right and left in a random way so that it's hard to predict. And if we apply very small perturbations, we can stabilize this orbit so that we can keep the orbit only to the right side. The theory that has been developed in the 90s on chaos control could achieve this. But we also applied this same theory that we developed to the problem like this. So the goal of the control here is to avoid the extreme events. And this model has 40 variables. The top left panel shows that 40 variables in the vertical axis, and the time goes to the right. So I'm showing all 40 variables values like that, and it evolves to the right. And this time shown here is 1 year equivalent time series. And we identify twice a year extreme events. So we run the model for 100 years and identify what's the threshold for twice a year extremes. So the goal of this control is to avoid these extreme values occurring. So whenever we predict that this extreme value happens, we apply some small, tiny perturbation to avoid that happening. And what we did at the bottom, to avoid the rightmost, the highest values, so that blue is a histogram of 100 years, and we could achieve perfectly in this case to avoid these extreme events. So if you can apply this method to the real weather events, for example, the heavy rain, and if you see some threshold heavier than some threshold, to avoid that, we could possibly apply the same theory to the digital twin of the Earth. And here we tested this idea with a typhoon. So typhoon develops to make the circulation more intense so that it's a storm developing. And we try to reduce the development of the storm. So the right panel shows two curves. One black one is the case without control, so that we have the more intense tropical cyclone. So here, lower, more intense. And the green is after we applied this control. So we could effectively reduce the intensity. Similarly, in this case, we simulated the real disastrous heavy rain event that happened in July 2014 in Hiroshima. And the left panel shows the heavy rain occurring in Hiroshima city. And after we apply very small perturbations, then this we could change in a desired way, so that we could avoid the disaster. So these early studies led to convince the Japanese government to establish this moonshot goal number 8, that's basically developing the methods and technology to control and modify the weather, particularly for extreme winds and rains, by 2050. So the Japanese moonshot research and development program aims at the goal by 2050, and we started this research like 3 years ago, and I'm appointed as the program director to supervise this activity in Japan. And there is an IEEE spectrum article. So if you are interested in more details, you could take a look at this. And after that, more recently, this year, I found time to focus on more theoretical study to expand how we can really control the unpredictable events, so because of chaos. And so this paper was recently accepted for publication, will appear maybe in January very soon. And the main finding in this paper is this duality principle between data assimilation and control. Data assimilation is for the prediction, and control is to control. So I will not go into details, but I found this duality principle so that this can give us an understanding why we could control the weather or the highly chaotic systems based on our understanding of the chaos synchronization. Okay, towards the end of my talk, so I will introduce more of what we have been doing beyond the weather prediction. So we try to generalize the concept of prediction so that the theory and mathematics behind the prediction can be used in a wide range. And of course, the computation is really essential in this prediction. And if we think about the future of the computer design, the architecture, so far at RIKEN, we had the K computer in 2012 and Fugaku in 2021. It's about 9 years. And we aim at 2030 for the next Fugaku. So the next machine, as far as I understand, will have a lot of GPUs and good for more focus on the AI type of computations. So we cannot live with the current design of the software for the weather prediction or other type of the simulations and data assimilation. So we need to think about how to combine this, our approach on data assimilation with this new AI and machine learning approach. So I draw the schematics showing that model richness on the vertical axis and the data richness on the horizontal axis to the right. And these two methodologies cover the different domain like this. So by combining these two in a good way, we could push the boundary of the application so that we could predict the phenomena that we are not be able to predict at this moment. So AI and machine learning can do much better than the traditional numerical weather prediction methods for the case where we have no physical understanding, but we have rich data. And data assimilation can be expanded the domain towards those directions. So we have been doing a number of research in different topics, and this is related to the weather. This is a typhoon-induced storm surge modeling, but using the machine learning method. So the top panel shows the typhoon, the statistical method to predict a storm surge. And this is apparently different from all the others. And the second row is based on the numerical weather prediction model. So this is what we have better than the statistical method. But the bottom three are based on the machine learning. So now these machine learning methods can produce much better prediction similar to the numerical weather prediction in a much simpler way than the whole numerical weather prediction model. And the second example is this tsunami inundation prediction. So the input to this machine learning system is the observation data at the sea bottom of the offshore sea bottom. We have 200 sensors, about 200 sensors offshore Tohoku region of Japan. In 2011, we had a severe earthquake in Japan. And the left panel shows the physical-based model prediction of the tsunami flow depths. So the red is higher tsunami depth. And the right side is the emulator, the machine learning emulator of that. But it's not computing the full model equations. We just use the sensor data, 200 sensor data inputs, and produce only the coastline flow depths. And this is quite accurate and much faster. So for tsunami, it's very important to have fast computation because the speed is very fast. We need to produce the prediction in 1 minute or something. That is essential to save the lives and properties there. And another thing is this combination of data assimilation, numerical weather prediction, and AI machine learning methods. So because we have big data from this remote sensor, the phase array weather radar, we applied the convolutional LSTM for prediction. But the convolutional LSTM can take the inputs of the future data, but we don't have access to the future data usually. But we have an independent numerical weather prediction system that can produce the future data. The future data means the future radar image. And these are not perfect, of course, but this is useful. So if we push this data into the LSTM and train, then we can produce, of course, the best result. The right panel shows the skill higher the better, and the dashed red curve shows the best skill. And we also looked at the global precipitation data based on satellite sensors. So the bottom panel shows the observation image. Because of the satellite path, we see some artifacts of the satellite path. But this is well predicted by the AI and machine learning because this learns the data from that. So the top panel shows the AI machine learning prediction. And the middle panel is our traditional nowcasting system based on the motion vectors. So we can capture the motion of the observed image and then try to extract to the future. So that's the second middle panel. So clearly the AI machine learning method can produce better skill, much better skill than this traditional tracking algorithm. And we also work on combining data assimilation, some components of data assimilation with machine learning. So one challenge is to build this simulator for the observation. So we simulate the Earth's atmosphere, and the atmospheric conditions are described by temperature, humidity, or those atmospheric variables. But the satellite sensors observe the radiance top of the atmosphere. So from the satellite sensor, we see the Earth. Then we can see how bright in certain wavelengths of the light, like infrared, if this is an infrared sensor, or the microwave, some wavelengths. And we see how bright is this, the Earth look like. So that's what the sensor observes. So there is no direct relationship with the sensor data to the atmospheric conditions. So we need to have this operator that converts the temperature, winds, and humidity to the observation data from the satellite. And we can build this by our physical understanding of the radiative transfer equations of the Earth's atmosphere. This is very complicated atmospheric science. But if you have a set of the atmospheric analysis or forecast with the actual observation data, without any knowledge about the radiative transfer of the atmosphere, we can build a machine learning-based operator that converts the atmospheric state to the observed satellite data. So this is known as a satellite simulator, and this is necessary if we treat this satellite data in data assimilation. So we have a successful case, and we publish this. We also go beyond what we could possibly do using the physical radiative transfer model. We are now developing even purely machine learning approach to build this satellite operator. And another topic is this machine learning-based weather prediction model, but for the regional scale. So we would like to have a very high-resolution regional weather model. And the main problem, for example, I showed the case that we use Fugaku for the real-time prediction for the small-scale weather. And that required Fugaku. And this is a very expensive system if you think about the actual application in the society. If we always need Fugaku, that's too expensive. So if we can replace that forecasting model with a machine learning model, then this can accelerate the computation significantly, and the price becomes more feasible. So now we have the global machine learning model. So we take the low-resolution global forecast from the machine learning global model and use it as a boundary condition. And we tested different methods to combine the boundary data with the internal high-resolution data to produce the forecast of the high-resolution small domain data. And so far, we found this method shown here to combine two data, like aggregate the low-resolution data with the high-resolution data to produce the future high-resolution forecast work the best, so that we compare with the ground truth, and it produces a high-resolution image very well. And another thing that we explore is to use the data assimilation to improve the AI surrogate models. So the AI surrogate models relies on the training based on the analysis trajectory. So we have an access to, for example, the ECMWF global analysis data. Then we can use those data for training. So here, it's a little bit complicated, but the blue dashed line surrounded box shows the first data assimilation step. So the problem setup here is that we have a perfect model. We never know what is a perfect model. And we generate the observations based on the perfect model so that we have a ground truth to compare with. And using these observations, we use the imperfect model to do data assimilation, producing the analysis trajectory. So that mimics the real situation in numerical weather prediction, that we have an analysis trajectory first to train, in this case, the LSTM, or any kind of the machine learning model that works. So using this analysis trajectory, we train the LSTM, and then use this LSTM to assimilate the same observations again. So that's the optimization loop part. So that's a purple dashed box. So then we produce the updated analysis trajectory that's supposed to be better because our LSTM is trained on the analysis trajectory that should be better than the initial imperfect model. So we can repeat this loop until convergence. Then we could get optimized LSTM. And we found that this optimized LSTM, the bottom left shows the model error. And we started from the leftmost column, that is the imperfect model. And the first generation of the LSTM and the optimized LSTM on the right. So the blue is lower error. So clearly showing that this optimization loop works so that we can produce better analysis trajectory for the better surrogate model. And another thing is to apply machine learning method, deep learning method for data assimilation. So here we applied this deep Bayesian filter that assumes that we have a latent space that we can build. The latent space dynamics is completely linear. That helps data assimilation very much because the linear dynamics guarantees the Gaussian distribution stays Gaussian forever. So this approach works very well when we observe very sparsely. So the left column shows the case when we observe those black dots. Those are pretty sparse if you think about the size of the world. But still, the LETKF is a standard approach of the ensemble Kalman filter, and the deep Bayesian filter produces lower error. The lighter color is lower error. And on the right, we observe even more sparsely. So those dots are like that. So very few observations, and the deep Bayesian filter works much better. Basically, at this observation coverage, LETKF doesn't work very well. We knew that because it's too few observations. But this deep Bayesian filter finds the latent space. That's a low-dimensional space that describes this dynamics of the atmosphere. So it's well constrained by this latent space, so that if we find the proper state in the latent space, that can produce the better prediction. We also applied data assimilation in the ocean. I will skip the details, but this is also a typical problem on data assimilation with the ocean, and we produced the analysis data. So we could produce the ocean model based on this analysis, and we can do much more based on this. And also we are interested in the ocean ecosystem prediction, particularly the small domain, in this case Tokyo Bay red tide prediction that affects the fishery, fish farmers basically along the coast. And we apply the approach based on the simulation with a lot of measurements, the local sensor data, so that machine learning is effective for this type of prediction. We also applied data simulation with this forest simulation system. So the goal is to simulate every single tree in the world, but it's very challenging, of course, and the monitoring is difficult. What we have is this satellite observation on the right that observes the leaf area index, how many leaves in that unit area, and basically how green it is. And we have this data every 4 days at 1 kilometer square mesh resolution. And we apply this to achieve a very well simulated, based on each individual tree simulation, to represent this leaf area. So this helps the forest management and also the control. And COVID-19, we applied during COVID-19 period our data assimilation method to estimate the parameters of this simple model based on most reliable data. Those are the yellow box data. Those are the hospitalized, the recovered, and the death numbers. And it works very well to estimate this effective reproduction number that represents how, what is the situation of this pandemic. And another thing is to collaborate with biological scientists. In this case, we apply data assimilation based on the Kalman filter to estimate the force acting between cells, so that when the cell deforms, there must be some force acting between the cells. We could observe only this camera image, so that tells where are the junctions of these cells. And this method worked very well compared with the previous methods, so that we could estimate the force very accurately based on these camera image data. Okay, so these are all, not all, but some of the examples that we have explored in RIKEN to establish the concept of the prediction science. So if we think about what's the current situation of numerical weather prediction and machine learning, so we use this top left part, the observations and the physically based model to combine with data assimilation to produce the analysis data that is very well structured data for training. And we could train the neural network and basically emulate the reanalysis data. That can produce better forecasts than the current numerical weather prediction model. That is happening now. But in the future, so there are a number of attempts of the research to take the observations directly to the machine learning, not through data assimilation. Then we could have a latent space based on our physical model, or to capture the physical structure of the system. Then within this latent space, if we can do the conditional sampling based on the current observations, we could do the full Bayesian estimation. That's the ultimate goal of data assimilation and numerical weather prediction. And that can produce the fully Bayesian prediction of this complex high-dimensional system. If this is possible, I will lose my job as data assimilation scientist, but this is what I hope that will happen in the future. Thank you very much for your attention.
So thank you for a great talk. So now it's time for question and answer. So if you have any question, please come to the one of microphones. Okay.
Hi, David Brown from Berkeley Lab. I was interested in your discussion. By the way, thank you very much for a fascinating talk. It was very nice. Your discussion about control of chaotic dynamical systems. And I can certainly understand what you're probably doing computationally, but if I understood correctly, you're interested in actually controlling the weather. Can you say something about how you'll use that information to do that?
Sure. So we have a theory, but the challenge for the controlling the weather is the actual facility or implementation, how we can operate those facilities to produce proper perturbation in the atmosphere. And that's a challenge. One typical method is flying the aircraft to put some seeding materials in the sky to modify the clouds. And the early studies so far found that if we can operate this aircraft in a proper way, using this understanding of the chaotic dynamics, then we could potentially reduce the intensity of tropical cyclones, or even change the direction of the tropical cyclones, or modify the intensity of convective rain clouds. So that seems most promising so far.
Okay, thank you.
Thank you.
So I have a question from online.
Okay.
So as you explore diffusion-based Bayesian estimation, how do you prevent the generative sampling from drifting into dynamical inconsistent atmospheric states? Are you integrating physical, prior, or dynamical constraint?
Sorry, I couldn't catch what was the question.
Oh.
Maybe easier to see it.
Yeah, please see it. Oh.
No, I cannot see. yeah.
Very difficult to control.
Yeah. Diffusion-based Bayesian estimation. Yes, how do you prevent the generative sampling from drifting into dynamically inconsistent atmospheric states? Okay. Yeah, diffusion model seems very promising, but assuming that we have sufficiently large data set to build the latent space in a proper way so that any sampling on the latent space will lead to dynamically consistent state. So that requires a lot of data in my understanding. And that's a challenge. So the question relates to the case when we have insufficient data so that some sampling can lead to dynamically inconsistent state. In that case, we need to increase the data. I think that's necessary. Or we might be able to design something better than the diffusion modeling. So any type of the latent space and the conditional sampling on the latent space should work.
Okay, thank you.
Okay, thank you.
So let's thank speaker again.
Thank you very much.
So let me move second talk. Mark Munsell leads a non-profit effort to expand the geospatial theory ecosystem in St. Louis, Missouri. Previously, he held positions with National Geospatial Intelligence Agency, including Chief Artificial Intelligence Officer, Director of Digital Innovation, Chief Technology Officer, and Deputy Director of Chief Information Officer and IT Service Directorate, where he managed a multi-billion-dollar development budget. So in all of his roles, Mark facilitates innovation development aimed at transforming and modeling software engineering and artificial intelligence technology to better serve its mission partners, as well as overseeing and streaming IT-related capabilities and services. So please welcome Mark.
Hey, good morning, everybody. Very happy to be at this conference. Welcome to my home city, St. Louis, Missouri, born here at a hospital that was knocked down many, many years ago. So just to give an indication of my age, the biggest indication of my age is that I just recently retired from the National Geospatial Intelligence Agency last May, where I had the last role as the Chief Artificial Intelligence Officer of that agency. Previous roles were the Chief Technology Officer and a variety of other technical and operational jobs over the years. I always get a kick out of trying to understand and see how well the signers can sign National Geospatial-Intelligence Agency. I feel for them to have to spell that out with letters. It is one of the more difficult agencies' names to pronounce, and even more difficult to understand what they do. And so let me just give you a real quick highlight of what that is, who they are, why it's important to St. Louis, and why I am talking to you about it today. Many people are familiar with the National Security Agency. You've seen it in the movies, Central Intelligence Agency. You know that the National Security Agency listens. They wear headphones, they turn knobs. A lot of people think of them as the ears of the country. They're listening. The best way to describe the National Geospatial Intelligence Agency is that we are the eyes of the country. We're watching. We're not watching you, watching our adversaries. And in doing so, we have this sort of tradecraft, we call it, or this domain of technology. We use the term geospatial technology. And it's a class of a lot of things. Obviously, it's remote sensing, but it's also what we call a geographic information system, so points, lines, and polygons. It's Google Maps, right? It's using GPS. It's using artificial intelligence to derive insight from massive petabytes and hundreds of petabytes of data. This agency holds the world's most extensive volume of the photographic record of the planet. At a resolution, of course, that's classified. But what do we do with that data? How do we manipulate that data? How do we exploit that data? What kind of insights we get from that data heavily, heavily relies on automation. And that's what I'm going to talk to you today about how we use automation, what the problems that we face in dealing with this data, this remote sensing data, most of this data coming from low Earth orbit, but other orbits as well, and how we use high-performance compute to be able to solve those problems. Hundreds of terabytes of imagery come down today from a variety of different commercial sensors, national sensors. You guys know that companies are constantly launching more and more satellites to do communications. Our downlink capacity now is massive and growing. Amazon just announced their new project, going from Project Kuiper to Project Leo as a commercial product, more and more capability in space, more and more Earth observation happening from space, dozens of companies getting into this business, equates to more data, not necessarily more information or more insights. It's interesting, coming from the government, how easy it is to sell the United States Congress on a piece of kit, on hardware. God bless you guys, it's a hardware conference, right, mostly. Showing them a satellite and saying, this is what the satellite will do for you, they get out their checkbook. It's a sexy thing, it's a cool thing, it's like a, it's a gearhead kind of thing. It's easy to convince people that we need to put more satellites in orbit. It's very difficult to convince them that we need to process that data, exploit that data, and do important things with that data. That's why we're putting the satellites up, not just to fly satellites. We're trying to get insights from that data. That's the hard part. It's kind of the unsexy part, and it's the part that I had to deal with most of my career. Just a quick chart. I know at the bottom it says not for redistribution, so please go to TerraWatch, subscribe to their website. But this is their sort of prediction of commercial and some governmental satellites that are going up specifically to do Earth observations. Right? Let's talk about that class, not all the other satellites that are going up. So more and more and more satellites, more and more data, more capacity, faster flow, but still not able to solve this problem of gaining good insights, good information, exploiting that data to do useful things, to solve not just national security problems, that's kind of what the domain that I come from, but to solve agricultural problems, transportation problems. Even, Wall Street bets on this data. It's one of the consumers. If they can get a tip, if they can get some insight on something that's happening somewhere in the world, seconds, minutes before everybody else, that's important to them. They'll make bets based on that satellite data that they subscribe to. So what are we talking about in terms of the kind of data? We're all familiar with the electro-optical. It's what humans are able to see in the visible spectrum. It's the most loved, most common, most used by human analysts. Next would be infrared or near-red. What's interesting about this, you've seen this in the movies. You've seen it when the predator's flying over the jungle. We see the bad guys. They light up in the dark. You can see them move around. That same technology, that near-red and infrared technology, is the same technology that agricultural scientists use to detect unhealthy crops. Synthetic aperture radar, more and more companies launching SAR satellites. What's special about that? You can see things at night, see things in the dark, see things through clouds, cloud belt around the world. around the equator is very troublesome. Many times, many of the locations that we would want to see are covered by clouds the majority of the time. And then, of course, multispectral and hyperspectral, all kinds of ways to turn the knobs to change the understanding of the signatures that you're seeing to detect radiation, chemicals, a variety of other signatures through multi and hyperspectral. So these are some satellite modes, some remote sensing modes. Now we're moving into the opportunity to combine those modes together for the sensors. In some cases, putting the modes together on the same satellite, the sort of core bore that you're looking through, that's very difficult to do, mostly by combining those modalities on the ground, data centers with high-performance compute. But the real breakthrough is being able to not just fuse those modalities, fuse it with other data, like I mentioned before, points, lines, polygons, any kind of data that is derived for space and time, but be able to combine those together with multimodal AI models. And let me just give you an example of what the opportunities are there. So when we think of multimodal AI, a lot of people think, of course, computer vision, eyes of the country. They think of audio, ears of the country. But text still rules the bureaucracy of the United States government. When large language models came around, and they said, hey, there's promise here with these things to be able to generate reports, read reports, generate spreadsheets, generate PowerPoint. Should have heard some sighs from anybody that's participated in the Department of Defense, Department of War, excuse me, as the main language of the Department of Defense, PowerPoint. So large language models should be able to chew those up, spit those out, make our life great. But what's cool about those models is that for many, many years, analysts write reports. That's what they do. They majored in government, they majored in political science, they majored in some sort of softer science, not computer science or physics like the folks here, but are writers, presenters. They brief the president. Their goal is to generate text that conveys important information, intelligence reports, millions and millions of reports of text that are associated with pixels on an image. And so now you start thinking about multimodal AI to be able to associate that text with that image and use that approach is something very powerful. Now think about if you have images of the Earth, go back 30 years, high resolution, and you have expert humans that have described those images in great detail in text, you have something very, very valuable. What are the different applications of this technology? I mentioned some already. Obviously, national security and defense, where I come from. Agriculture is a huge one. Transportation and logistics. Human health. Tracking patterns of humans associated with disease, whether it's just doing sort of research on disease that we track from hospital records, medical records, or whether it's mobile disease, COVID, trying to track the spread through mobility. Disaster recovery and relief. This technology, geospatial technology, is extremely important in planning as well as recovery. Utilities, urban environment and forest planning, business marketing, ad tech. I don't know if you know what I mean by advertising technology, but you guys know that this thing right here, this is a pixel, so it's Google. I say good things about Google in this briefing. Them tracking you and where you're at, the spatial aspect of where you're at. There's a business in Google Maps. It's to get you to go to the right place. There's great benefit to humanity to get you to turn at the right time in the right place. It saves 50 cents in gas. It saves you 15 minutes of frustration of driving around and being late. It's trillions of dollars that we save as a globe using technology like Google Maps. Just so happens it's very useful if they know where you're at, because they can serve up the right kinds of advertisement to you in spatial context. That takes a lot of compute to do that, too. Uber, Lyft, all of that stuff, when you talk about tracking billions and billions of devices, entities associated with people or any other sort of association, that takes a lot of compute, high speed, storage, and networking. Let me give an example of a company that does this, and they do it well. The company's called Planet. They've been around for a while. Got great friends at Planet. This is one company of, let's say, a dozen that are imaging the Earth for a variety of products and solutions. What was special about Planet was their desire, their pledge, their approach to image the entire planet every day. That's remarkable. Even in my agency, where we're all about this, we would have never have dreamed of doing, attempting, saying, pledging to do something like that. And they come very close to doing that. They have hundreds of satellites, hundreds of petabytes of historic data, which, by the way, that's the problem here. It's not really the ability to take photographs from low Earth orbit. That's becoming easier and easier and cheaper. What's difficult is storing that data and doing something useful with that data. And the kind of compute that it takes to process that, especially with these new models. So it's a massive bottleneck. Good friend of mine, the old former director of the National Geospatial Intelligence Agency, had some folks do some math for him and said, we would need to hire 8 million analysts to be able to analyze all the imagery that's available today. So not just the national imagery, not just our country's imagery, but all of the imagery that's coming from commercial and the ever-increasing amount that's coming. It's just too much data. Humans can't do it. You guys know what the solution is. Of course, it's automation. Of course, it's artificial intelligence. The class that is most common, the class of artificial intelligence that we use the most, is called computer vision. You guys are familiar with it. I saw some great presentations this morning of very specific computer vision problems about how to analyze video of people doing real world things, like chopping up food. I don't know if you're here for that this morning. That's a very hard problem for a computer to understand and be able to understand it in some level of detail, right, to make it useful. So this trend of going from words to worlds, from being able to use artificial intelligence behind the glass to using artificial intelligence in our global reference frame in the environment of the real world, is kind of the big emerging thing in geospatial AI. We use classic machine learning a lot, modeling, clustering, regression, classification. You guys have seen that maybe in some of your school books where you are classifying fields, using segment anything to be able to get outlines of objects, chaining that together with other computer vision models to do object detection. And then, like I mentioned just earlier, this idea that we can use frontier models, large language models, OpenAI, Anthropic, Google, interface those with existing systems, APIs, agentic AI, to be able to have these models learn how to use geospatial tools, this domain, geospatial databases and APIs. It's interesting, some of the early testing that we try to do with frontier models to ask it geospatial questions. Mapping is still really confusing to these big models. OpenAI came out with their model just a couple of months ago, and somebody asked it to make a map. Of course, all the states are wrong, the names are wrong, the misspellings of everything. It's still something that's, there's still a ways to go, right? When these big frontier model companies are going for accounting, law, medicine, the big money makers, right now, like mapping and spatial context and doing things on a globe, like just measuring distance from one latitude, longitude to another one, it gets it wrong. It gets it wrong. It doesn't know how to do those sort of measurements. So this is an emerging thing of how do we train, how do we change, how do we fine tune, how do we build models that are specific to solve these geospatial problems. And that lower right-hand corner graphic is really kind of what's emerging right now. We have some great partners that are working on this, that are working on solving problems with high-performance compute. One of the best known in this environment is Oak Ridge National Laboratories, not just having a record of, or history of having some of the most powerful computers in the world, they have some of the best scientists working on some of these difficult geospatial global Earth observation problems with us. Here's a great example. You might not have thought about this, but you guys know you can use stereo imagery to get depth when you look at it, and have the sort of two vectors coming together, get some 3 dimensions. If you have many, many images overlapping each other, many, many different rays coming together, you can develop a high-resolution 3D data set from the massive amounts of overlapping imagery taken from different angles. Now imagine having hundreds of petabytes of high-resolution imagery, and you're able to apply supercompute power to that, run it for months at a time. You can build the highest resolution terrain model of the Earth, which is very valuable. And so this is something that they've been working on with us for a while. And this new product that they've come out with is something that's very valuable to the United States. And NGA is very happy to have them as a partner. Gravity. This is important as well. I don't know how important you think gravity is to you in your daily life. I know, again, you use this thing, you use the accelerometer on this thing. This thing has like a magnetic model on it. When you stand on the street corner, it actually calculates the declination for you, so it adjusts true north to your phone's magnetic north. That magnetic model is fed by plenty of other models, geodetic models, we call them, gravity models. Help make that magnetic model that you use on your phone. Gravity models are very important when you're launching something from one continent to another on a known trajectory. It's very important to know the sort of gravity signature underneath that so you can adjust that trajectory. It's very important to have that high accurate gravity model available to you when you're flying an airplane, long distances where you might not have GPS and you need to use inertial navigation system. So another great product by Oak Ridge National Laboratories where they use massive amounts of supercomputers and 7,800 GPUs to help us make a better gravity model. Who would ever thought years ago, people making maps, that you would be able to use a massive database of Earth observation, satellite imagery, and high-performance compute to automatically detect every building footprint in the world. Back to the 8 million analysts it would take, it'd probably take 8 million analysts to map every building in the world. And to keep doing it, keep it updated. This is something we never even thought would have been possible 10 years ago. But with the advent of really good artificial intelligence models, really good high-resolution databases, and more importantly, really good high-performance compute, we're able to do such tremendous feats with the Oak Ridge National Laboratories. Let me get a little bit closer to home. There's something special here in St. Louis. Besides having the National Geospatial Intelligence Agency here, and having that agency contribute to about $1 billion to this economy. And let me explain that real quick. Congress appropriates money to the Department of Defense, War. They allocate a certain budget to the National Geospatial Intelligence Agency. And then the National Geospatial Intelligence Agency has a certain amount of work here. About a third of their work here happens here in St. Louis. So that's about 100 companies that work in that. Several universities, some new institutes. The Taylor Geospatial Institute. The Taylor Geospatial Institute is here in St. Louis. That's a consortium of about 8 universities. I'll talk about that in a second. There's another activity called the Taylor Geospatial Engine. Have several programs. One of their most intriguing program is this Fields of the World, where essentially they put together a pipeline, artificial intelligence pipeline, to be able to discern and automatically create field boundary database of the world. Again, these are problems that you might not think about in your sort of dinner table talk, but these data sets are extremely valuable to not just countries who are trying to understand what their capacity is, what their food security is, but they're also very important to companies that are trying to do business. This product has recently been launched, and now the Taylor Geospatial Engine has a variety of other products that they're working on. These are mostly open source projects, and this kind of data can be usable by any researcher. And I would ask you to reach out to the Taylor Geospatial Engine, Google them, look them up if you're interested in this kind of work. So this is all changing. Since the invention of transformers in 2017-18 and all the massive amounts of investment in large language models and frontier models, some of the biggest companies that have been in Earth observation already are starting to take all of those new discoveries and put them into new, created from scratch, geospatial foundational models. So the same kinds of energy, investment, and funding that would go into the next Claude or the next ChatGPT, well, maybe not the same, maybe not hundreds of millions or billions of dollars, but the same kind of research and expertise and interest in investment are being done by companies like Google, by IBM. And I want to tell you a little bit about those. So Google this summer published a new product called Google Alpha Earth. Obviously, Google has been in the geospatial technology realm for a long time with their maps business and other Google Earth, right? Google Earth Engine sort of came after that. Now Google has taken that whole team. Oh, did you see that? Was it nonsensical before, or did it switch? Let me go back. OK, so it's some sort of new language there. Anyway, I'll vouch for what it says. That underlined piece where it says go DGF, whatever, it was highlighting the word embeddings. So along with the invention of transformers, this idea that same idea, except you're using pixels for the embeddings, and you basically get a vectorization of pixels. And what you have is a signature that you can use. You have a fingerprint, essentially, of patterns of pixels that you can query and get results from. Here's another example. OK, for some reason, this text is OK on the right side. IBM and NASA teamed up with their model called Prithvi, and at the Jülich Supercomputing Center, really amazing work by some of the biggest companies in the world to solve these massive, global, ubiquitous Earth observation problems. All of these are public. Much of this is public domain. Much of this is sort of open source, donated to the world. And a lot of people now are taking the results of this research, and applying it to their research. For example, the Taylor Geospatial Institute, covering universities all the way from University of Illinois. Dr. Bill Kramer's here, front row, making sure that I do a good job. He's the one that prodded me into this. To the University of Missouri and all the universities in between. St. Louis University, Washington University here in St. Louis does some of the world's best medical research. Taylor family, you may not be familiar with the Taylor family, who's sponsoring this work from St. Louis, philanthropists in St. Louis, also the owners of the privately held Enterprise Rent-A-Car. So you might have used Enterprise Rent-A-Car this week, and we here in St. Louis thank you for your business. They did something cool this year. They teamed up with Amazon Web Services and put out a challenge this last year, the Generative AI for Geospatial Challenge, where they had dozens of companies apply, and they offered a prize of $1 million in compute to novel ideas, novel approaches to sort of cross generative AI to solve geospatial problems. One of the companies that won that is a company called Bedrock Solutions, which is a startup company. So I just showed you Google, kind of a big company. IBM, kind of a big company. And from all of this energy, all of this attention, and much of it here in St. Louis, sponsored by the Taylor Geospatial Institute, we have startups that we are sponsoring in this area, which have done some very novel things. Again, a multimodal foundational models focused almost solely on geospatial information. They have a product. I'm about to show you a video demo of one of their products. We talked about embeddings before. And so this is a no-shot, low-shot example of automatic classification, object detection, and classification of objects. Here you have barges. And what you have on the right-hand side are classification mapping of those objects. And it puts those objects into that classification space. You see the person drawing, highlighting clusters of objects on the right mapping, and returning very similar objects on the left. These are boats, certain types of ships. Again, no data labeling going into this. This is the model itself, able to classify those things, group those like things, cluster them. And in this case, if you did want to review that, if you did want to draw polygon around those things and say this is this type of object, you can greatly increase your efficiency in terms of doing, there's aircraft carriers, greatly increase your efficiency of labeling objects or finding a specific object. Just a handful of low-shot training examples, and you stick it on hundreds of petabytes of data and say, go find me an object like this. So especially if it's a very rare object, one that's rarely observed, like say in North Korea, this would be a very valuable tool to be able to find that rare object in petabytes of imagery. So it's happening here in St. Louis, and that's kind of my message to you today. That's why I'm here today. I want you to know about St. Louis. I want you to know about this geospatial technology that is a hub here in St. Louis. I want you to stand up and salute the flag with the arch in the background because it brings it all together. The only thing I'm missing here is beer and the St. Louis Cardinals. There's hundreds of companies in this. This is my very crude way of spilling out all of these countries or companies that are involved in this ecosystem here in St. Louis. Many of these companies support the National Geospatial Intelligence Agency, but they also support BEAR. They support the Danforth Plant Science Center. They support U.S. Transportation Command, which is about 20 miles to the east of us. And I want to play this video for you that sums it all up.
For the past 80 years, the course of our nation's security has been charted here in St. Louis by the National Geospatial Intelligence Agency, helping position our city for greatness, innovation, and impact. Just 5 years ago, the GeoFutures initiative established the geospatial ecosystem that has helped elevate St. Louis as one of the country's centers of geospatial technology. Anchored by NGA West, St. Louis has built a growing talent pipeline and strong academic partnerships. As NGA prepares to take the next step in its evolution, our geospatial ecosystem is establishing a new shared blueprint for success that will guide the next phase of our growth. To start, we are setting a new North Star for our ecosystem to position St. Louis as a world leader in geospatial innovation. We'll drive that innovation by developing our workforce for the jobs of today and tomorrow, accelerating research and development, strengthening our businesses and entrepreneurs, and showcasing our region as the global leader it is destined to be. And we are capitalizing on geospatial artificial intelligence, the engine of the future. With the world's largest investment in GeoAI right here at NGA, St. Louis is uniquely positioned to lead this change. This isn't just a plan, it is a new course for our future. A future anchored by the new NGA campus and built on shared ambition. A future where the world comes to St. Louis for solutions. A future that is STL made.
I'm Mark Munsell. If you want to know more about geospatial technology, you want to know more about what's happening here in St. Louis, hit me up on my LinkedIn there, and I'll be happy to engage you. And take any questions.
Yes. So if you have any questions, please come to one of the microphones. Yes.
One of the things you talked about, the great data sources, are all these things flying in Earth orbit. There's a whole lot of them. What role do you see for geospatial technology in helping to manage all that space junk and AI to help us not have all those things crashing into each other?
No, it's great. In fact, I did have one example that I did not put in here. There's this other, managing it is important, right? And modeling satellites and orbits and sensors, being able to understand and predict where they're at any given time to be able to manage traffic, that's something very important to NGA, National Reconnaissance Office, Space Force, all of that. So I would say that there's this other aspect of us looking from Earth up that will also be very important to geospatial technology. And that is something that, while certainly there's concern, and I know our astronomers out there are already starting to complain about how busy the night sky is, there's still this sort of big sky little airplane thing that's happening. I think we still are decades away from real trouble. What keeps me up more at night about satellites and orbits are many of these orbits are 95 miles, 100 miles up. And I don't know how long it takes for a missile to get from the ground to that, but it doesn't take long at all. In terms of creating space junk, that's what needs to keep you up at night. Yeah.
Thanks for the talk. I'm curious if you're using classical optimization algorithms in your work, or is it just machine learning? By classical optimization, I mean objective function and constraints.
It's a good question. It's not my work. All the work I showed you today are researchers that are here in St. Louis. It would be a great question for them. I wish I had them here with me and be able to answer those questions. Some of this is sort of classic work. I mean, we've been doing computer vision since computers. So It's obviously gotten more sophisticated, especially in the last 7 years, way more sophisticated. But I can't answer that question for them, because to be honest with you, I summarized hundreds of models and thousands of researchers and work to do it. Yeah.
So like if I'm from a private company, who would I talk to try to find out?
You could start with me, and I will feed you to a variety of different entities that you could talk to. Yep.
Thank you.
Yep.
So we have one question from online. Could we push more of this processing and automation towards the edge of potentially reduced amount of data ending up in duplicative centralized repositories?
Yeah, no, it's a great question. So it's, can you push more of the processing to the edge? And so, of course, that's a big demand. So especially for warfighters, they, in some cases, if they want a computer vision model, they might be looking for something in the field there that day that they observe that has never been observed, potentially. And so they would want to take a photo of that, train a model of that, like right there in their Humvee, and then push that data up or to models either on drones or to satellites or other sensors on the ground. But the obvious progression of this would be to put both the processing and the models on the sensors as far down the chain as you can, or up the chain as you can, including putting GPUs on satellites and doing as much processing as you can in space. And I think that's a natural evolution that's going to happen.
Okay.
Bill, you got one? Or are you just going to take this opportunity to walk out? I thought maybe that's what we're doing.
Thank you, Mark.
Yeah.
I wanted to see if you could describe a little bit some of the other types of uses of the information that you're using for national security. So, for example, some of that information I know went into the world's biggest tree census, automated AI tree census, also flood inundation, things like that. How does that impact, or how does that impact what will be happening in the future, and what types of computing does that need?
Yeah, so I mean, it really applies to so many different things. Anything that you can sense, either from space or from aircraft or terrestrial, right? With the right kinds of models and the right kind of investment, you can detect, change. You can detect failures. You can predict crop failures. So trees. I don't know if you know how much money the world spends on tree maintenance. It's a lot. I'm talking like urban maintenance, much less massive sort of forest maintenance and planning. So there are, I could go back to the slide, there are so many applications for this. That's why there's a lot of investment in this. There's so many different ways that you can use this data that people haven't even thought of yet. That's why there's a lot of ceiling to this whole domain, but I'll caveat that with the venture capitalists that are out there that might be running back right now and wanting to send me an email. Spying is still the #1 customer of this. There's a pretty good gap between national defense and then commercial applications. This commercial application piece is growing more and more. There is money to be made here, but there's still a pretty big gap. And it will take some of these frontier companies. It will take OpenAI, Anthropic, Google, IBM. It will take some of these companies to get bored with making too much money in pedestrian domains like accounting and law and medicine, to get into more of the types of approaches like climate and other food security and other Earth observation goals.
Thank you.
Thanks.
Okay, let's thank speaker again. And this is the end of the great 12 invited talks, so that I'd like to thank all the invited speakers and attendees. Thank you very much.